In the last video, we taught the machine to read. It can clean text, count, and even deduce importance. What can't it do? Well, everything else. We don't and can't use words when we don't know their meaning, unless you're a pseudo-intellectual. If I say the bank is closed, is that a river or a financial institution? Using our older methods, the word bank is just a token, and its meaning and context is lost. This difference is called the semantic gap, and bridging it is where the true magic of AI begins. Today, we're the beavers, and our wood to build this semantic bridge is called Word2Vec. Word2Vec transforms words into a vector, which is a list of numbers. However, unlike our older techniques, this one captures meaning, something we all strive to achieve. How does it do this? Word2Vec works by training what we call a neural network to guess a word based on its context. Let's imagine the machine is reading a fantasy novel. The context here are the words throne, crown, castle, and kingdom. The model's job is to take these four words and try predict one word. In this case, the output could be queen. This technique is called continuous bag of words. The inverse order of this is called Skip-Gram, where you take one word and try predict the context words that would surround it. In reality, these network layers are much, much bigger. If the fantasy novel we're reading had 50,000 words, there would be 50,000 one-hot encoding vectors put into the input layer. The hidden layer is what learns and stores the word vectors, which is their meaning. Then the output layer calculates the probability of the correct word being guessed. We'll cover neural networks in future videos, so for now, don't worry about the complexity. The core idea is simple. Words with similar contexts will have similar vectors. For example, if you could replace queen with king or monarch, and the context words still make sense, this means that the vectors must be very close together numerically. This closeness is what we call cosine similarity. We've established that the words king and queen have similar semantic meaning and therefore similar vectors. This means that they are plotted close together on a graph. A word like banana has no business here. Its vector is completely different as its meaning is completely different. Cosine similarity essentially measures the angle between word vectors. The smaller the angle is, the closer the similarity of words. So, king and queen have a small angle, whereas the difference between king and banana creates a large angle. This is how a machine sees meaning. We can prove that vectors hold meaning with vector arithmetic. We start with the vector for ManCity. Then we subtract the vector for success, removing the component of recent dominance and trophies. Then we add the vector for nostalgia, or past glory. Learn from the text about a historically great but currently inconsistent team. Now, what do you think this calculation would equal? You guessed it, the resulting vector points closely to Manchester United. The model learns that the difference between the modern-day dominant City and the current United is ultimately a difference between success and nostalgia. Now that we have vectors for individual words that capture their meaning, we need to bridge the gap again. This time, we create vectors for entire sentences. Word2Vec allows the machine to understand the meaning of each word with separate vectors. But how do we capture the meaning of one specific sentence? This technique is called average Word2Vec, and it does exactly what it says on the tin. Say we wanted to capture the sentence meaning of this sentence, the bank is closed. We would do this by simply averaging the vectors out. The equation is to add up each vector in the sentence that you want to capture the meaning of, and then divide it by the number of vectors in that sentence. In this case, we add these four vectors up, and then divide it by 4. This calculation would give us sentence meaning. Let's think back to our initial problem. The bank is closed, having ambiguous meaning. Now, if the surrounding text of the sentence vector mentions river, the machine knows that we're talking about a river bank. Whereas if the surrounding text mentions money, the machine knows that we're talking about a financial institution. And with that, thanks to Word2Vec and average Word2Vec, the machine can now understand the semantic meaning of words and sentences. We've successfully built the bridge over the semantic gap. That's it for this video. Thanks for watching. If you enjoyed and want to follow me on my journey to understand the machine mind, please don't forget to like and subscribe. I'll see you in the next one. Stay tuned.